Hello friends, myself Gautam Gupta and I am a Master's in Structures and did my BTech from NIT Allahabad and currently I am associated with iGate Chhattisgarh. Today, as many of the students, they asked me, sir, we have some doubts how to design or what are the combined foundations. So, for your benefit, I am just uploading a little bit something on combined foundations. So, when we see combined foundation, what is the first thing that comes to our mind? That is, why it is needed? What is the need of the combined foundation? And the second thing, if we are needing it, then how we need to design it? As we know, foundations, they are just an intermediate structure that are transferring the load from a superstructure to the soil. So, the soil should have necessary bearing capacity to transfer or to resist the load. Now, as we know that if we have a frame structure, in a frame structure, the load which is coming from the superstructure, it should be transferred by means of a foundation onto the soil. So, the soil which is below the founding level, it will resist the total pressure from the superstructure. Now, as we told you, what is the need or why it is needed? As you can see, there are two number of columns, column A and column B. If these two columns, they are placed very close to each other, then there are chances that the foundation system for column A and the foundation system which I will be making for column B, this is the foundation system, this one. So, there are chances that the foundation system of column A and column B, they will overlap each other. So, if they are overlapping each other, then instead of providing an isolated footing, it is always better to combine both of them. For another example, suppose this is the property line. Everybody of you might be familiar with this particular name, Abhishek, and this name, Salman Khan. So, I know that you can identify what is the surname of this particular person. Now, if you see in this particular property line, suppose the property of Abhishek is this portion, property of Salman Khan is at this portion. Now, Abhishek wants to make a structure with two number of columns, column 1 and column 2. Now, the size of the foundation which is coming for the column 1, suppose it requires this much area, and for the column 2 it requires this much area. Now, what is wrong about it? Can we see that Abhishek foundation is okay, it is going in the property of Salman Khan. So, will the Salman Khan allow it? Will the Salman Khan allow it? Yes or no? No. Definitely, you will not allow a person to come to you in your property and to make his own particular structures. Why? Because you have paid for it. So, what will Abhishek do then? Abhishek will, okay, he will not intrude in the Salman Khan's property. So, I am just removing this particular part. But there was some necessity of the area. Some area was required so that the load can be effectively transferred. So, we have to increase this area. So, if you have to increase this area, what we can do is for column 1 and for column 2, instead of intruding into another's property, we can provide a combined footing like this. Now, combined footing can be of rectangular shape as well as it can be of trapezoidal shape. This is the trapezoidal shape, 1, 2, in this form. Generally, the trapezoidal shape combined footing is provided wherever we have a very large difference in the load coming on first and the second column. So, as we can see from this particular diagram, the load on column is quite large compared to load on column 2. So, this is a basic reason why we need combined footing. Now, after learning why the combined footing was needed, now we are coming on to our next step, that is how to design a rectangular combined footing. Okay. For a designing of a combined footing, there are few important points that we need to take care. All these points will be included in our design calculations. These points are: what is the given data, then sizing of the footing, then the necessary checks that are involved for the design of combined footing. In this checks, we have moment, one-way shear, and two-way shear. Two-way shear, it is also known as the punching shear. Then reinforcement, and finally the diagram. So, all these steps will be included in our design calculations. Okay. Again, given data, sizing, checks, that is the moment, one-way shear, two-way shear or the punching shear, and reinforcement, and the final diagram. Now, for an elementary profile of a combined footing, just see here. Suppose this is the first column line, this is the second column line. I will be making the elevation as well as the plan view. This is the elevation view. Just placing the columns. This is the plan view. In the elevation view, the information that will be done or used in the design calculation, it can be represented as: this is the force P1, this is the force P2 coming on column 2. The distance of the outer edge of the footing from the center line of the column 1, representing it as small a. The distance from the center of the column 2 up to the edge of the foundation, representing it as small b. And the center to center distance between the column, we will represent it as small c. Now, I have, for general purpose, I have considered a square column. We can say that the column size is C1, the column size for column number 2, it is C2. That means this dimension is C1, this dimension is C1, this dimension is C2, and this dimension is also C2. Now, this total length, representing it as capital L, this total width, representing it as capital B. Okay. So, this is a basic elementary profile of a combined footing. This is the elevation view and this is the plan view. Now coming on to the design steps. The design, we will be using the limit state method, which is based on Indian Standard Code 456 2000. I will be listing down all the design steps. So as a student, you should clearly understand the abbreviations that we will be using. So first one, that is the given data. In the given data, generally the examiner, he gives you the following data of load, then the column sizes, then the distance between the columns, the bearing capacity of the soil, grade of the concrete, reinforcement, and some few more parameters. So P1 kilonewton, P2 also provided in kilonewton. In the question that you are provided, you have to always check if the load given to you are factored or unfactored. For our case, I am considering that P1 and P2, which are the external loads coming on column 1 and column 2 respectively, they are unfactored loads. So I will just write unfactored. Okay. Now P1, P2, C1, that is the column size, generally given in mm, C2, column size 2, generally given in mm, then small c, it is the center to center distance between the column, generally given to you in terms of meter, then SBC, that is the soil bearing capacity. The soil bearing capacity is given to you in kilonewton per meter square. Apart from this data, there are chances that in a question, the examiner also provides you with the projection beyond column 1. That was represented as small a. So small a can also be given in the question in terms of mm. But if they are not providing small a value, you can consider it approximately 600 or 700 mm. FCK, that is the characteristic strength of concrete, either they will be providing M20, M25 or something. So I am representing it in terms of Newton per mm square, or the megapascal, any units can be given to you. Then Fy is the yield strength of the steel reinforcement. Generally Fe415 or Fe250, that is the high yield stress deformed bar or the mild steel, they are given to you in the questions. So it also has a unit of Newton per mm square. Now, as we will be doing the calculations based on the limit state, so there is a factor of safety that we have to use, okay. We will call it as a load factor of safety. So I am just writing it as FOS equals to 1.5. So this is the basic data that is provided in the question, based on which we have to design the combined footing. After writing all the given data, now second step is the sizing of the footing. By sizing, we mean that we have to determine what is the capital L, that is the entire length of the footing, and what is the transverse width, that is capital B. The sizing of a footing is done based on two conditions. The first condition is that the CG of a rectangular footing should match with the center of gravity of the loading. This is the first condition. And the second criteria which will be helpful for sizing is the SBC. the area required, it is given as load P1 plus P2. This load, which is the unfactored load, that is the summation of the load coming on the two column, it is increased by a value of 10% to account for the foundation weight. So to increase it by 10%, I am multiplying it by 1.1 divided by, this load needs to be transferred onto the soil. So this is divided by the SBC. So when it is divided by SBC, we will have a value in terms of meter square. So A required is into meter square. Now the second part, the second one, that is the CG of the footing. This is the center line of the first load. This is the position or center line of second load. This is distance A, this is distance C, this is distance B. From the column 1 center line, the load CG is represented at this location, that is at a distance of x bar. This x bar value is calculated as P2 into C upon P1 plus P2. So from the edge of the footing, from the left side edge of the footing, what is the distance of the load CG? This is the load CG. What is its distance? A plus x bar. This A plus x bar, which is the load CG. So the CG of the load should match with the CG of the footing. CG of the footing, this complete length was L. That means from the left end, this value should be equal to L by 2. So A plus x bar should be equal to L by 2. Now, from the given data, if we want to check which was the unknown, we know the value of P1, P2, SBC. So we know the value of A required. We know the value of P2, C, P1 and P2. So we can calculate the value of x bar. From calculating x bar, then we can calculate the value of L. Now, this will give the value of L. I am writing it in terms of meters. So as we have provided a rectangular footing means the area required will be equal to length into width. So this A required value, B, that is the width, into length equals to A required. A required has been calculated, L has been calculated. So from here we will also get the value of, B. So now this is the part of the sizing. So we have easily calculated L and B. Suppose the dimension that you are getting for length, suppose that you are getting a value of 5.37 meters. Always remember, whenever we are providing a footing, it should always be in multiples of 100. So instead of 5.7 or something, 5.73 something, it is always better to give 5.8 meters or 6 meter, something like that. Never give a fractional value. So this is how given data and sizing are being utilized. After completing the given data and the sizing, we will come to the third point, that is force calculation. Force calculation involves the drawing of bending moment diagram as well as the shear force diagram. Just to brief you again, till now we have not utilized in any of the part the load factor of 1.5. So we will be drawing and calculating the forces BMD, SFD, everything based on the unfactored condition. And later on, when we will be doing the moment or the shear check, we will be adding the load factor of 1.5. So, force calculation, as I told you, it involves the bending moment diagram as well as the shear force diagram. Now, if I draw the elevation view of the combined foundation in terms of a line diagram, this was column line 1 having a load P1, column line 2 having a load P2, and this distance small a, C, B. Now, this load of P1 and P2 is being resisted by the soil, converting the pressure coming onto the soil in terms of a UDL. So, let us apply a UDL in this manner. This UDL has the intensity of W in terms of kilonewton per meter. The total structural system should be in equilibrium. So, this W, which is acting over this entire length, that is capital L of the footing, should be equal to P1 plus P2. So, W, which is the UDL, it is given as P1 plus P2 divided by this total length was L. So, this value we can calculate in terms of kilonewton per meter. Now, if you see this particular figure, it is just a form of a rotated table, the table that you might have in the colleges, something like this. And this is the reaction R1, R2, and this is the loading. So, what is this now? This particular structure is representing a overhanging beam which is having two number of supports. This overhang, this is the overhang, and the distance between the center of the support can be represented in this form. In the lectures of the structural analysis, we have already seen how to draw the bending moment diagram and the shear force diagram. So, I will be directly drawing the bending moment and the shear force for this particular structure, which is a form of a overhanging beam. Now, so this is how you have calculated W. This is column line 1, column line 2, P2, P1, A, C, B, and there is a UDL of intensity W. So, just below this structure, we will try to draw the shear force and the bending moment diagram. So, the shear force diagram, the basic principle of shear force everybody knows. This is distance A. So, for a UDL, the shear force, it will be an inclined line. This value, this particular point, I am writing it as 1. When we approach the point 1, there is a load of P1 which is going down. So, I will move the line downwards. It comes to this point. I will represent this point as point number 2. Now, again after this point, there is a loading which is going upward direction. So, again this is moving upward. This point at which the shear force is 0, I am representing it as point number 3. This as point number 4. After point 4, there is again a load of P2 going in the downward direction. This one. This is point number 5. From point 5, again a load going upward, meeting at this point. So, this is the shear force diagram, and we have mentioned 5 number of points. that is point number 1, point number 2, point number 3, point number 4 and point number 5. Similarly, if we want to draw the bending moment diagram, it is drawn based on the deflected profile due to the loading. As we can see, this load coming on the portion A, this will try to sag the foundation. So, if it is a sagging, okay, so bending moment, since it is a sagging, I am drawing the bending moment on the tension side. This is the sagging. This will also sag the beam. So, this is also sagging, and this particular portion, it will try to hog the beam. This one. Most of you might have a doubt that why we have made this particular type of diagram. So, just to see, this is the foundation system. Okay. So, the deflected shape will be something like this. In this shape. So, this is how it will be deflected. So, from this particular diagram, we can visualize that this is a sagging portion, this is a hogging portion, this is a sagging portion. And we know that in sagging, the tension comes on the bottom face, and in hogging, the tension comes on the top face. For our calculation purpose, we basically require 3 number of points. I am representing this particular point of the maximum sagging moment as first. This point, which is at a location 3, I am representing it as 3, and this point, which is at a location of 5, I am representing it as 5. So, in a force calculation for SFD and BMD, we have these many different values. So, just mentioning it, we have V1, V2, V3, V4, V5, M1, M3, M5. So, these are the unknown parameters that are utilized for SFD and BMD. So, value of V1, W into A, value of V2, P1 minus W into A, value of V3, 0, value of V5, W into B, and value of V4, P2 minus W into B. From here, we can get the values of the shear force at different points in terms of kilonewton. Now, from this diagram, we don't know what is the position of point number 3. The position of point number 3 is required for the calculation of moment at this particular point, which is the maximum hogging moment. So, let the distance of this particular point number 3 from the center line of the column, I am considering it as Z. So, from the edge of the column, the edge of the footing, this distance become A plus Z. At this particular point, at point number 3, the shear force is 0, hence, this value of 0, we can write it as, okay, I am writing SFD here. This value of 0, we can write it as WA plus Z, that is the force coming from the bottom equal to the force coming from the top. So, from this particular calculation, we can calculate the value of Z. So, once we have calculated the value of Z, now we have to calculate the moment. This particular part is acting as a cantilever. So for a cantilever, the moment is generally given as W into cantilever length square divided by 2. So this M1 is W into A square by 2. Similarly, M5 it is W into B square by 2. Okay. And for M3, moment due to this particular loading, A plus Z, moment due to P1. P1 and W, they are in opposite direction, so the moment will balance each other. That is P1 into Z minus W A plus Z whole square by 2. So these are the values of the shear forces at different points and the moment values at different point. These shear forces and the bending moment, they will be utilized for calculation of one-way shear, two-way shear, maximum moment, okay, and finally the reinforcement value. So I hope that all the 3 points told up to you are clear. As we have done the sizing, that is determined the length, determined the width and also calculated the forces. Now coming on to the other part, we will be calculating the thickness of the footing. For the calculation of thickness of the footing, there are different criteria. So we will be using one of the criteria that is also known as the two-way shear criteria or the punching shear criteria. Punching shear, it is calculated at a peripheral distance of d by 2 from the face of the column. So as you can see, this is the face of the column and we have just demarcated a red line at a distance of d by 2. So this particular portion, okay, it will be failing in punching. So that criteria we will be utilizing. This dotted line which is represented in the plan view, it is representing the critical section. So as this distance is d by 2, this distance is also d by 2 and the column dimension, suppose it is C1, the load if it is P1. So the total critical section width becomes C1 plus G. Now to use this particular section, we are using some approximations. Okay, our design that I will be providing to you, it is a relatively conservative design. There are many assumptions that I have considered. So for the students who are appearing in the university, okay, they can directly use this particular formulas which I will be writing here. Or if you want to go into some detailed calculation works, then you can refer standard books such as BC Purnima or AK Jain and other foreign writers. So now just see here. As we talk about shear that is represented as tau. This is your shear stress. Now, as per IS 456-2000, the punching shear or the two-way shear capacity, tau capacity, it is given as 0.25 under root FCK. There are other factors also, but for basic purpose, I am assuming it only is 0.25 under root FCK as we are doing the work in LSM, limit state method. This is the capacity which is based on the characteristic strength of the concrete, that is M20, M25 or any other grade. This capacity should match with the external shear which is generated by the load from the superstructure. So the load which is given as P1, this P1 is acting over a shear area. The shear area is in a form of a wall. Okay, like this is the part that is being broken off due to the punching. So this area, this area, then there might be this area also, this area. So all the area that is, we can call it as the area of the wall. So this shear area is given as 4 times C1 plus D into D. Small d is known as the effective depth. Effective depth means the complete depth, that is capital D, that is the complete depth, minus some cover. So if we remove this cover, this part, that is the cover to the reinforcement. So if you are removing from the total depth the cover, the remaining part becomes small d, that is known as the effective depth. So it is based on the effective depth calculation. So the external shear that will be generated due to this load, it is P1 upon 4 C1 plus G into D. As you remember, I told you that we will be utilizing the load factor, that is 1.5, in the later stages. So now it is the time to utilize that particular 1.5 value. Why? Because we are doing our analysis in limit state method. Moment, shear, torsion, all of them are known as limit state of collapse or the factored limit states. So I will be multiplying 1.5 also. The value, the unit of this particular value, that is tau capacity, it comes in kilonewton, sorry, not kilonewton, Newton per mm square, and this also we have to apply the Newton per mm square. So accordingly you have to change the units of P1 and D and C1. So if we equate both of them, that is 0.25 under root FCK, if this value is equal to P1 into 1.5 upon 4 C1 plus D into D. FCK we know, C1 we know, P1 we know, so the only unknown remaining is small d. So small d we can get in terms of mm. This particular calculation, since we are using combined footing which is having two columns, column 1 and column 2, so the check should be performed for calculation of the effective depth on column 1 as well as on column 2 also. So when we will be utilizing this particular check in column 2, for column 2 we will be changing this value. So this value will be changed, it will be equal to P2 now. This value will get changed, it will get C2, and similarly corresponding formulas will also change. So out of the two depths, that is based on column 1 and column 2, whichever is maximum, you have to provide that value. In most of the calculation, if you are getting a value of 300 or 250, something like that, but if the loads are heavy, it is always recommended that you provide the effective depth size approximately equal to 450 mm. So as a general rule, you can take 450 mm as the minimum depth. Okay. Some people can take it 500 also. Okay. So I hope that till now L, B, D and the moment and the shear force diagram, everything is clear to you. So after doing the sizing, that is L, B and calculation of the depth, now we come down to the moment check. Moment, as you know, we have calculated three moments M1, M3 and M5. So these moments should be less than the moment carrying capacity of the concrete. So moment carrying capacity given as MRC. Whenever we are designing any particular section, we always design a section as a balanced section or under reinforced section. Over reinforced sections are not designed. So, the moment resisting capacity of the concrete, that is MRC, it is given as 0.36 FCK capital B into X into D minus 0.42 X. Now, here we know the variable FCK, we know the variable capital B, we know the depth, effective depth small d. But there is one more variable coming as X. X is known as the depth of the neutral axis. This depth of the neutral axis, X, will be taken as 0.48 into D for Fe415 steel grade, or it will be taken as 0.53 effective depth for Fe250 steel grade. So, based on this particular formula, we can calculate the MRC value calculated in kilonewton meter. Now, as we know that we have calculated the external moments, M1, M2, sorry not M3 and M5 at point 1, 3 and 5. But these external moments were unfactored values. Okay. So we have to multiply these moments with a load factor of 1.5. So this multiplied with 1.5, this multiplied with 1.5, this multiplied with 1.5. And these external moments should always be less than the MRC value that we have calculated. So if all of them are satisfying these conditions, that means we have provided a sufficient depth to take care of the moment. But if any of the calculation goes wrong, means suppose the value of this particular condition, it is not satisfied. So if it is not satisfied, then what can you do? You have an option of increasing the effective depth of the footing. So you can easily increase the effective depth of the footing and do the recalculation. So just removing this part again. So we have checked the external moments against the moment resisting capacity of the concrete for a balanced section. Now, based on the external moments which are actually acting on the footing, we will be calculating the reinforcement also. So the reinforcement, it is calculated by the formula MRT equals to 0.87 Fy AST D minus 0.42 into X. Now, the value of AST that we need to calculate, that is the area of the tensile steel. For calculation of this, instead of MRT, we will put either M1 into 1.5 or we will put M2 into M3 into 1.5 or we will put M5 into 1.5. And from this equation, Fi is known, value D is known, X is known. What is unknown? It is only AST. So from here, we get a value of AST1, AST3, AST5. So this is the area of steel based on the moment. Now, the code, IS code 56-2000, it has some set of criteria for the minimum reinforcement. So the minimum reinforcement criteria, AST minimum, it is 0.12% of capital B into capital D. This particular value is used for Fe 415 and
0.15% of B into capital D. B into D, that is the overall area or the gross area, or FE 250. So all these values, that is AST1, AST3, AST5, all these values should satisfy the minimum criteria. So this is how we perform a moment check. Based on these AST values or the minimum reinforcement, we calculate the number of bars as well as the diameter of the reinforcement. So, number of bars, suppose it is n. We will take a standard spacing. Generally, the spacing that you can take is somewhere between 150 to 200. So the number of bars, okay, I will give it. So the number of bars n is given as d upon spacing. Okay, I am doing some of the approximation, so I am telling you the general way so that you can easily perform in your examinations. After calculating the number of spacings or the number of bars, n into pi by 4 phi square will give you the value of area of steel. So, area of steel, as you know, you have calculated, n you are calculating here, so you can easily evaluate the dia of the bar. Generally, the size of the dia of the bar, reinforcement bar that you are providing, you provide 16 mm, 20 mm or higher. Now, this minimum reinforcement is also provided in the transverse direction. Transverse, that means in the direction of capital B. After completing the moment check, the only check we are left with is the one-way shear. As you know, the code specifies that the one-way shear should be checked at a distance of small d, that is the effective depth, from the face of the column. So let us see this particular check. So sixth, that is one-way shear. Now, I am drawing the elementary shear force diagram which we had used in calculation of forces. This was the center line of column 1. This was the center line of column 2. Okay. Now, so the shear is calculated at a distance of d from the face of the column. That means from this point, that is the center line of column 1, center line of column 2. So this is the critical section. So from the face of the column, that means this distance becomes C1 by 2 plus B. Similarly, in this point also, on the right side, this distance also becomes C1 by 2 plus D. Here, this is the critical section. So this becomes C2 by 2 plus G, and here also this distance becomes C2 by 2 plus D. So all these lines which we had done at the D distance from the face of the column, they are the critical sections where we need to check the shear. This value, suppose this is Vs1, this value Vs2, this value, this is Vs4, and this value Vs5. All these values can be calculated by using the principle of similar triangles. Why? Because we know the value of V1, we know the value of V2, we know the value of V5 and V4. So we can easily calculate these values also. Now, when we talk about the one-way shear is calculated along the width B. So, this is the section. Okay, this was your column. So, from the column face at a distance of small d. So, this particular section has a width of B and the effective depth of small d. So, this is the shear area which will be resisting your external shear. So, the resisting shear area is given as B into small d. So, the external shear stresses, they will be given as tau external 1, tau external 2, tau external 4 and tau external 5. So these four shear values we need to calculate, and it is calculated as Vs upon your shear area. This value will give you a unit in Newton per mm square. So after calculation of these external shear stresses, this external shear stress should be smaller than the values based on the Polar coefficient. So the Polar coefficient says that the one-way shear calculated by the external stresses should be less than the maximum value of the shear given by the concrete grade, that is tau E should be less than tau C max. This tau C max is calculated based on table 20 of code, and it is based on the concrete grade. So this is one of the criteria. And the second criteria, it is tau E shall be less than tau C. This tau C is calculated from table number 19 of the code, and the value, it is dependent on the percentage reinforcement as well as the concrete grade. If any of the check is failing, then the option is either to increase the depth or to increase the steel reinforcement. There is a factor, mistakenly I have not written. Okay, I'm just including that particular load factor also. For tau E, when we are calculating Vs upon shear area, this Vs value should also be multiplied with a factor of 1.5. Now, coming on to the final diagram. This is the elementary profile of the foundation. We have calculated three areas of steel, that is AST1, AST3 and AST5. So, at this particular location, where we have a sagging moment, in the longitudinal direction, we either provide AST1 or the minimum reinforcement. For the hogging part, we provide AST3 or the minimum reinforcement. And for this part, this is also the sagging part, we provide AST 5. So, representing it as AST 3, AST 5, and AST 5. Friends, always remember that they should satisfy the minimum reinforcement criteria. Now, we are also providing the reinforcement for the transverse direction. So, for the transverse direction, the reinforcement is always provided on the inner faces. And when we see the front view, we will see that the transverse reinforcement will look like circles. So, if we want to represent this particular reinforcement in the plan view, at this location, this is AST1, at this location, this is AST5, and on the upper face, this reinforcement, this is AST3. And the transverse reinforcement in the plan view, it will look like this, provided along the entire length. So this one. So this is the elementary diagram. But always remember, whenever you are writing the values, you should always write the spacing or the number of reinforcement bars and the dia of the bar. So I hope, as we have done the combined foundation, I have given you the basics of it, like how to calculate and everything. So now you will be able to solve any type of problem. So this was a rectangular foundation that we have done. Similarly, there is a trapezoidal foundation also, for which you can refer the other lectures. So friend, if you have any doubt or if you want to give any feedback, it might be positive or negative, you can contact me at